Sometimes sets can be quite large. In fact, sets can contain an infinite number of values. And especially in such cases, we might wonder if there's a nice, compact way to express that. So let's consider an example. Consider the set of non-negative even numbers. So we know that non-negative means just not negative. So 0 is actually an even number, believe it or not. 0, 2, 4, 6, 8, 10, 12, 14, 16. We can kind of see the pattern in this set, but we have to use these little ellipses to indicate that the set just kind of goes on and on. And normally we can look at them and we can kind of figure out what the next element is in that set. But is there a better way to write this? Can we write this more compactly? And we have something called set builder notation, which sort of builds the set through a construction of some sort. And the way we often do that is using something that looks like this. So notice that this is still a set, it has the set brackets, but it's the set of all elements, which we don't have to use x, but it's just a common variable. So it's the set of all elements, and this little bar here means such that. And what that means is what's on the right of that such that is information about what kinds of x will live inside of that set. So that some statement involving x is true means that we are going to give it a qualifier and a quantifier, perhaps, if we're dealing with numerical values. So in the example of 0, 2, 4, 6, 8, well, one thing that we know about even numbers are multiples of 2. Another way to write that is you can, if a number is even, you can divide it by 2 and still get a whole number. Or you could factor a 2 out. So if I look at the elements of this set, well, the reason 0 is even is because 0 is 2 times 0. 2 is 2 times 1. 4 is 2 times 2. 6 is 2 times 3. And 8 is 2 times 4. So the commonality among all even numbers is that they're divisible by 2, that you can factor out a 2. All right, so I'm going to write this set of even numbers as the set of all elements, and again, I don't have to use the letter x. X is just kind of the template for the definition, but I'm going to say that this is equal to the set of all x. Now, I don't know anything about x based upon just what I've written down so far. I have to give this a greater explanation. So it's going to be the set of all elements x such that, or where, the property that x is equal to or can be factored into 2 and some other number. Those are the even numbers, all numbers that are 2 times some integer. Okay, but now I haven't really specified what n is either, right? So now I'll put a little qualifier in there where n is an integer I'll say a non-negative integer. And now I've fully described all even numbers, because every even number, you can factor a 2 out of it, and then the other factor is going to be, something like, it could be 0 or 1 or 2 or 3 or 4. It really just depends on the even number. But every even number can be described in this way. We just don't know what that other factor will be. It depends on how large that even number is. Now I could write this even more compactly. I could use a notation. We could say x is equal to 2n, where n is an element of the set of integers, which is the reserved symbol for that is a capital Z with this extra little leg here, this extra little support bracket, if you will. And I only want it to be the non-negative integers, so I can also say something like, I can say something like n is greater than or equal to 0. Okay, so maybe that isn't more compact, that's a little bit more symbolic, and that means exactly the same thing. So Z is the set of all integers. That's a reserved symbol. That's across any mathematics course, that symbol means the same thing. Let's take a look at another example. Write the set of elements 3, 7, 11, 15, and so on in set builder notation. So one thing that I see here is that there's a constant increase of 4 among these elements. And also, I see that would be a linear progression. It's a linear function in there. So I could say that all of these numbers are going to be 3 plus 4 times some natural number, some whole number. And for example, 3 is 3 plus 4 times 0. 7 is 3 plus 4 times 1. 11 is 3 plus 4 times 2, and 15 is 3 plus 4 times 3. So that gives me a way of writing this infinite set. The next element would be 19, 23, 27, and so on. So I'll express this set as the set of all, maybe just to not use the letter X again, maybe I'll just say the set of all elements called J. Okay. Now, tell me about J, such that J is equal to 3 plus 4, I'll use K, where K is a whole number greater than, or I'll just say GE, greater than or equal to 1. I'm sorry, greater than or equal to 0. So once again, I could write it similarly here. I could say, instead of where K is a whole number greater than or equal to 0, I could say that K is an integer. And it can't be any integers because integers could be also negatives. So I could say K is greater than or equal to 0. So I'm basically listing all these tidbits, all these facts that must be true. And it's a very rigorous definition because there would be no confusion as to what elements do and don't belong, since I've made sure and I've described every single symbol in that statement. Now, to really see the power of this, there's also a set of numbers called the rational numbers. And that symbol, surprisingly, is Q. That's the set reserved for kind of this extra little curve here. And it stands for really quotient. Rational numbers are defined as the ratio of two integers. So here are some examples. And the problem is you can't even begin writing this set out because there is no first element in that set. Right? And even between, say, 1/2 and 1/3, there are infinitely many fractions between them. So it becomes kind of complicated to even list out the elements of this set. So from just this description, I certainly couldn't get a sense of, well, what would be another element in this set? It's not concrete enough. So the set of all rational numbers could be described as the ratio of two integers, m divided by n. Again, you don't have to use m and n, it could be x divided by y, or they just have to be different, right? Because the numerator and denominator may or may not be the same. And by the way, a whole number, like 1 is a rational number, because you could write it infinitely many ways as 1 over 1, or 2 over 2, or 3 over 3. Same thing with 2, that's a rational number because it's equal to 2 over 1, and that's still a fraction involving two integers. Such that, okay, so what do I need to describe here? Well, I need to describe what are m and n. Well, m and n could be any integers, so I'll just say m comma n, belong to the set of integers. Now, it doesn't have to be just positive or just negative. It could be positive, negative, or 0. But wait, if the integers, and maybe I'll give a more explicit description of the integers here. Unfortunately, you can't write these in set builder notation, but you could write it like this. You could say 0 plus or minus 1, plus or minus 2, plus or minus 3, etc. So all whole numbers from 0 to infinity, positive or negative. So from negative infinity to positive infinity, I guess, would be more valid to say. But this is a nice compact way to write it. So since they can be any integers, I also have to be careful about the 0 because I can't divide by 0. And by the way, 5 divided by 0, let's say, is undefined. So it's not a number, and we just said that a rational number is a number. Oh, undefined is not a number. And therefore I have to also add this statement that n is not equal to 0, because anything divided by 0 is not a valid rational number. And that fully describes the set of all rational numbers. And now you can begin generating a list of them. It's just impossible to list them in ascending sequence because of the fact that between any two rational numbers, I can always find another rational number. The idea is, imagine a number line and there are infinitely many fractions, say between 0 and 1. And if I give you, let's say, 1/3 and 1/4, or I'll make this a little bit simpler, let's say between 1/3 and 2/3, well, there's a lot of space there. How do you generate a number that's between them? Well, one way to do that is to figure out what the average of these two is. So if I take 1/3 plus 2/3 and divide by 2, 1/3 plus 2/3 divided by 2, now that's still a rational number because, as we're going to see in a second, this is 3/3 over 2, and when you divide a fraction by a whole number, you could write that denominator as a fraction. And so here's a number between those. It would be 3 over 3 times 1 over 2, which is 3 over 6. So right here, there's 3 over 6, which is really just 1/2. And we could do the same thing for 1/3 and 3/6, for example. 1/3 plus 3/6. Find the average of those two numbers. All right, this is 2 over 1 from the get-go. 1/3 plus 3/6. 1/3 is 2/6 plus 3/6 is 5/6. Divided by 2 over 1 is going to be 5/12. And so halfway between here, you have 5/12. And you can see that this can continue on forever. Even though we're going to visually run out of space, we can kind of zoom back in and see that, again, we could create an infinitely wide gap between any two rational numbers. And therefore, it's really necessary to be able to write this in set builder notation for sets that can't otherwise be described in the element-wise form. So there are two forms, two ways to describe a set, so far, anyway. One way is in element-wise set. So list elements, right? Like we did with, here we had an element-wise set. And then now we've just learned this new technique, which is the set builder notation. And this compacts the elements.